Welcome to this tutorial series on scalability. In the last tutorial we were looking into caching and caching strategies. Today we are going to look into caching and cache invalidation. This is Balasubramanian. So what is cache invalidation and how it is different from cache eviction is what we are going to look into. So why a cache has to be invalidated? Cache data has to be invalidated so that the fresh data is getting served and the stale data is not getting served. That's the main one of the purpose or the main purpose that we can say. Evicting the cache data is also important to ensure the latest data, the latest cache data is getting warmed up and frequently accessed data is served with the latest version of the data. Less frequently or infrequently accessed items when kept in the cache would add to the size of the cache. Since the cache data is stored in memory or in the RAM of the machine, the size of the RAM, the requirement of the RAM size would increase if we keep infrequently items, and it would add to the budget, the overall budget or the cost of the caching strategy. We also need to understand that the cache refresh is not same as the cache eviction. Both are two different topics, but both come under cache invalidation. So what is cache refresh? Cache refresh is done so that the latest version is available. Cache eviction is done to ensure the optimal size of the caching engine. These are two different things. Cache eviction can happen in the background by caching system itself. There is no manual process which is required, but cache refresh could happen via a background process, or we can write code to ensure the cache is refreshed. These are two different things, and we want to understand that as well. So what will happen when a cache refresh fails and what will happen when a cache eviction fails, we will look at it. When a cache refresh fails, right, the clients, the customers who are consuming the cache data would see the older version of the cache data. It would create business problems, but it ensures the data is served, at least the older version. But when the cache eviction fails, it may end up in the new values not getting even returned to the cache because it might not have the enough RAM space to write into it. So we need to, this gives a clear differentiation between what is a cache eviction and what is a cache refresh or invalidation. There are different strategies for cache refresh. So we can refresh the data after each write. We looked into in the previous video that every time when a cache value is new value is written, maybe the cache data can get invalidated or thrown out, or the cache data gets refreshed also. We were looking into this in the previous tutorial, so please take a look into my previous video. So it's been told that there are two hard things in the computer science world. One is cache invalidation, the other is naming of things. This is told by Phil Cartland. He was a member of Netscape community. Maybe whoever has said, but this is a very hard problem, and that is why we are diving deep into what is cache invalidation and what is cache eviction now. Caching engines also provides out-of-box ways to perform evictions, and we would look into what are those ways which are provided out of box, or is there a way that we can do it or write a process to perform the eviction. We will look into this in the upcoming slides. So as we looked into what is a cache invalidation and what is cache eviction, we will focus only on cache eviction in this tutorial. Cache system would not have enough memory to cache all the data. As said, because cache uses the RAM data. The cache data is written to RAM, and the size of the RAM is limited. Maybe in distributed caches we can add nodes, but that would add to the cost. So we have to optimally utilize the size of the RAM. Many caching systems provide different eviction strategies, but we can broadly classify the eviction strategies into three. One is time-based eviction or TTL, time to live based eviction. One is access-based eviction and size-based eviction. These are the three categories. We will dive deep into what are those three strategies in this session. Caches, for example, when we are spinning out a cache node, we take it Redis, take it Hazel cache, take it memcached. We will spin up a new instance, and that is called as a node. The max memory of the node is defined. When no eviction policy is set, the new entries which are coming in may get ignored, and the size of the cache data reaches the end, the maximum RAM size of the node. No data is written into it. So that is what is the default eviction strategy for many of the caching engines. Redis. I may touch base on Redis during these tutorials, but it is a similar case for Hazelcast we can think of. Redis, a famous distributed cache, provides no eviction as a strategy itself. It means that Redis will not put any effort to evict any of the old cache entries. As and when it reaches, it is up to us to plan how cache has to be utilized. And if it reaches to the size, if it reaches the threshold or the maximum size of the RAM that we want to utilize, the new entry which are coming in will get ignored and it will not be written to the cache. When the memory of the node, that's what we said, when the memory of a node reaches the configured value of the cache, usually the caching engine, or probably it reaches a threshold, the caching engine will perform the eviction. So that is what is classified into TTL based, access based, size based. That's what we told, right? We will look into TTL based now. Caches evicted based on TTL, it is called time to live strategies. When we add a key and a value, we can always say that the key and value lives for this much amount of time. It can be mentioned in milliseconds or seconds. Many caching engines provide different way to configure it, but let's say that it is mentioned as a second or millisecond. Usually, it is not in millisecond means it cannot be less than a second. It could be more than a second because it becomes very difficult to evict within few milliseconds as well. Some of the caching solutions may disable eviction by default to keep the value indefinitely as well. So by default, there is no TTL. If the TTL is not provided, the TTL is set to 0. It means that the data is will live in the cache memory forever. Cache can also be evicted when the cache entry is ideal for a specified duration or when the key is not read or written into. So, so what are the ways we can use time to refresh the cache? So it has to be based on access as well. It's not the time alone. Uh, let's look into it in depth as well. So why am I saying this? Time is not the only factor which is used to evict it, though it is mentioned as the time. But time plus access is what we would be using. Redis as a caching engine provides a volatile or all keys TTL as a strategy, which means any keys whose expiry has reached or less remaining time for the key to be lived are evicted or chosen as candidates to evict. So what is that? We'll look into it with an example. So suppose that if we are inserting a key as a person user ID and the personal data as a value, and we say that the TTL, the time to live for that key and value is 120 seconds, and lot many user keys are getting inserted. So at a point of time, right, we are reaching the node's threshold, for example, 100 MB or 200 MB, or when the time limit reaches to 120 seconds, Redis will run a background job which will scan through all the keys. What are those keys which are nearing the TTL, which is not being accessed after it is being returned to, are marked as candidates for removal, and then they will remove it. Uh, so first, whenever the keys are getting marked for removal only, when we try to access the key, it will not be available. The eviction of values in Redis or the keys in Redis is not deterministic. What does it mean? Redis will run a job, or most caching engines run this job like this. What are those keys which are nearing TTL will be marked, and the caching engine may evict it at any time. So it is not deterministic. But when it is marked for eviction, the data would not be served. Caching engine may choose to evict it immediately, or caching engine may choose to evict it at little later point of time. Later point of time doesn't mean hours, but it means that it's its own cycle, right? That's what we want to understand. If there are no candidates to evict, for example, if the TTL is set to 1 hour, lot many values are coming in, right? They are returned to the cache. Uh, And if there are new entries which are coming in, and when the caching engine reaches the node memory threshold, the new values will not get inserted. We have to understand. So whenever we are choosing a TTL based caching strategies, we need to keep the TTL in an appropriate way, or we need to model the size of the caching engine appropriately. Why am I saying this? We will touch base on some of the use cases like a session. Session values are one of the TTL based items for TTL based caching. We will touch base on that example later. We need to model the storage requirement of the caching engine in such a way that we don't run out, we never run out of memory as well. And the items are older items are getting evicted as well. This is one of the important things that we need to consider while modeling the cache. Time-based evictions are performed during periodic maintenance activities by caching engines. So what is periodic maintenance activities? So caching engine may have a background job which will wake up and it will run like a garbage collection process. It will mark all those entries which are candidates for eviction, and the keys it will get expired or the data gets flushed out. That's what is meant by periodic job. Um, so as we mentioned that TTL based doesn't work only with time, we can also combine the TTL based TTL plus the access based together in time based cache eviction strategies. So what is that we mean by this? So whenever we insert a value and we provide a TTL, simple TTL as 10 seconds or 1 minute or 2 minutes in that case, if the items gets accessed within the 2 minutes of duration, the TTL gets refreshed to another 120 minutes. So it means the TTL doesn't alone play a role there. So whenever the items are getting accessed frequently, and those items will survive for the next cycle as well, and those items which are not accessed during that 120 seconds will get evicted. It doesn't mean that when we specify for this example, if 120 seconds as the time to live, even if we access those the same key 10 times or 15 times or 100 times in that 120 seconds, that data will get evicted. No, that's not the case. TTL based will also work with the accesses. What we can say that there are two other strategies that we can combine with along with the TTL based. Expire after access duration and expire after write. These are two sub strategies that we can use for TTL. What is expire after access? If the data is mutated during that point of time. For example, if there is a data, which for example is a session data, we are storing that, but it is not getting read. So if the session is expiring and we just do a renewal of the session, but not that data is not accessed, but when the data gets renewed, there is a write operation which is happening that will refresh the TTL to extend the TTL to another 120 seconds. That's write based. And there is another access strategy is called read based or read or write based. Even if the data is not written to, but the data is read multiple times, every write will renew the lease of the TTL. It means the same TTL will not be counted down or decremented. The TTL gets the lease gets renewed every time. The lease will get to the next TTL is like 120 seconds. For example, if the initial TTL is set to 120 seconds, and if the data is read after the 60th second, next 120 seconds it will leave apart from the 60 seconds. This is called lease renewal in cache, so it will happen. Most of the evictions are not happening during read phase because when the cache items are read, it has to be served faster. So the cache evictions usually happen during the write phase or during the background job phase. These are the two times when cache eviction happens. Why it should happen during the write phase? When the cache engine, when the user is trying to, or when the underlying system is trying to write an item to the cache, when the node memory can reach the threshold. During that time, it may trigger, or it could trigger, not may, it could trigger the eviction process or the background job, periodic background job which is running, right? That could trigger the cache eviction. This is what we want to discuss about the time-based eviction. We will look into the use cases, but while before we jump into the use cases, we need to be clearly keeping in mind we need to model the cache engine size, or do the back of envelope estimation of the caching engine by keeping sure that or by making sure that the memory is planned accordingly, and we have to ensure that if the node memory breaches the threshold, the new data will get ignored. the purpose of the cache might not get served is an important point to be considered. Now let's understand the use cases for TTL based eviction. One, session tokens. Second, shopping cart, booking, seat reservation, bus, theater, room booking. All these things can be in the cache, and OTP, one-time passwords could also be kept in the cache. Let's look into the use cases little more in depth. Session, whenever a session token is given and it could be valid for 1 hour, 30 minutes, 45 minutes, that data can be kept in the cache because it was mostly never getting mutated, and it is read multiple times during that lease period. So, and whenever the lease period is expiring, we need to remove that item from the cache, or whenever the data is getting accessed, the lease period may get incremented to the next 60 minutes or 35 minutes or whatever the duration. So session data is a potential good candidate for time-based eviction plus the access-based. So we need to understand it's not just time-based alone. It's not that after 120 seconds, whatever data which is written, our session data which is written 120 seconds before, we will remove it. In that case, most of our emails will get signed out at a hard stop of whatever it is, 1 hour or whatever it is, and we have to keep signing in, and this will break the user behavior. So time-based alone will not serve the purpose. Time-based plus access-based is what we need to remember. Shopping cart data, it is a very interesting use case because shopping cart people may add more items as well. It is a candidate where items will get mutated. Why we are saying this is a special case? The items that are kept mostly in the cache are those items which are mutated in less frequently but accessed more frequently. When we choose an item to be cached, it means that the data mutation is at a slower rate, but the rate is at the faster rate. Those are the candidates for cache. This we need to be keeping in mind. But shopping cart is a special category that item may get mutated as well, but it will be kept in cache for serving the shopping cart data because there might be 10 items in the cache and maybe two items might get appended or one or two items may rarely get mutated. But the data has to be served faster to improve the experience of the shoppers. So shopping cart is a very good use case where the cart gets mutated as well, plus it has to be served fast. So shopping cart is a potential use case. Next comes the booking. So what do we mean by booking? Train ticket booking, hotel reservation, theaters, rooms, all the data, which any of the booking data can be kept in the cache for a certain duration, so that we can block that room or the appropriate seat for some time, and that gets served also. So that is a potential use case. One-time password. One-time passwords are something which is valid for 15 minutes. It's perfectly TTL based. How many ever times accessed is not the case. It is just based on TTL. It will get expired in 15 seconds, no matter whether it is accessed or not. Or it can also be combined with access based because once it is read, it becomes invalid. Second time it gets invalid. So it could be combined or it is perfectly based on TTL. It is up to the designer of the solution to keep what is the access strategy for OTPs. And these are the potential use cases where we can use TTL and TTL plus reference based accesses. So since we looked into what is TTL, we need to understand about how do we model the test for TTL. Inserting data with a few seconds. For example, how do we model the test? Because it is important, right? How do we go to production without testing? This is what we have not covered in many of the use cases, but I want to cover it here. So we need to insert data in few seconds with a TTL of about 30 seconds, and we'll try to access it after the TTL. And if that expires, it means that the TTL is working fine. So that's something which we need to do. And we also need to insert in bulk with a bigger TTL values to ensure that what is the threshold, at what point of time we are reaching the threshold, so that we can model the right node size as well. That is important, which I told, right? This kind of testing strategy also has to be arrived. Also, we need to come up with a small scheduler which accesses after the TTL is expired. For example, 10 seconds before the item is getting expired, 15 seconds after it passes the TTL. We need to try doing the schedule to understand that how the expiry, what is the time it takes for the caching engine to do expiry, whether it is absolute expiry, whether it is approximation based expiry. We will come to know so that we can model the cache very clearly. So these are the testing strategies that I would use to ensure how will I keep my cache data and ensure the cache data is sized properly and accessed properly. So with this, we will come to we'll take a pass on the first part of the cache eviction. We'll look into the reference based in the next tutorial.